Aloha, everybody. This is Gigi from Kauai Community College. In this video, I will give you an overview of sequences and series. Okay, let's get started. So sequences and series, I always get these two words confused when I'm talking, not just because I don't know what I'm talking about. It just, sequences and series just sound kind of like the same. Anyhow, so I want to really specifically point this out so that you can see what the differences are, okay? A sequence is a list of numbers. For example, 1, 2, 3, 4, 5, 6, 7, 8, right? Now, the first term, which we probably would denote it with a small lowercase letter, like a sub 1, meaning the first term in the sequence is 1, the second term in the sequence is 2, the third term in the sequence is 3, and so on. And the nth term in the sequence is n, okay? Now, the series is the sum of the infinite list of numbers. Okay, so the difference is sequences is just a list and series is just a sum of the infinite list of numbers. So if that's your sequence, then the series that we're looking at is 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? And then when we're talking series, we also pay attention to a sequence of the partial sums. Okay, what does that mean? That means the first sum, S1, the first partial sum is 1. The second partial sum is 1 plus 2, which is 3. The third partial sum is 6. And the nth partial sum would be the sum, and we would write it as a summation notation, sum of the k term, and it goes from 1 to n, right? So this right here, 1, 3, 6, and so on, is what we call a sequence of the partial sums. Does that make sense? Like S1, S2, S3, Sn, and so on would be the sequence of the partial sums. Okay, so let's take a look at sequences. When you see sequences, you may see them explicitly, meaning you can plug in the n to find that nth term. For example, in an equation is given to you, an is equal to n plus 1 over n. So all you do is just plug in the n, meaning a1 is 1 plus 1 over 1, that's 2, and a2 is 2 plus 2 over plus 1 over 2, and that is 2.5, or 5 over 2. And then a3 would be just 3 plus a third, or 10/3. And then a sub 4 would be 17 over 6, right? Now, with that said, your sequence is 2, 5/2, 10/3, 17 over 4, not 3, 17 over 4. And what do you think the next term would be? So the next term would probably be, if you follow the pattern, would be 5, and the numerator is going to be, I would say 5 squared, 25, plus 1 is 26, and so on, right? So what are we doing with sequences? Well, we may ask, what happened to this sequence when n gets really big? Okay, so when we take a look at the sequence on a graph, we would see a bunch of dots, right? And it has a pattern. And so we can think of a sequence as a function where your input will just be a set of natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? So we can see a sequence as like a function. Okay, so this is kind of like a function. So what happened when n gets really big? That's the question of limit, right? So limit, what is the limit of a sub n when n goes to infinity? And when we talk about limit, there might be a limit, there might not be. So we would say that the sequence converges if the limit exists and diverges if not. Okay, so let's take a look at the limit as n goes to infinity of the sequence an here. Okay, so if we get a common denominator for this right here, we would see that is going to equal to n squared plus 1 over n, right? Common denominator is n. Looks like infinity over infinity, right? And the important point that I said before was that we can see this as a function. Therefore, L'Hopital rule will apply. Okay, so we can use L'Hopital rule to take the limit because this is in the form of infinity over infinity, meaning take a derivative of the top and the bottom, and you have 2n over 1. And so when n goes to infinity, this sequence will grow infinitely, meaning the sequence will diverge. Okay. Now, another way that we see sequences would be recursive, meaning we have a way to find the next term based on the previous terms. For example, in this sequence, A1 is given to you, the initial value is -1 over 4. And in order to find A of sub n plus 1, which is the next term, you would take A sub n, the previous term, square minus 29 over 16. Okay, so that is a recursive sequence. It's given to you. So let's kind of list out the terms here. A2 is going to have to be A1 square minus 29 over 16, which is -7 over 4. So we're starting at -1/4. And then the second term is -7 over 4, right? And then A3 is going to have to be A2 square minus 29 over 16, and that will give us 5 over 4. And then A4 is A3 square minus 29 over 16, which give us -1/4. Oh, hey, look at that. We are repeating. So this sequence will repeat itself starting at -1 over 4, then -7 over 4, 5 over 4, -1 over 4, and it keeps going. Okay, so that is 2 ways that you could see sequences, right? Recursive or explicitly. And then let's take a look at sequences in series visually. Okay, so suppose you have a square with an area of 1 unit. Okay, now what are you going to do with this square? You are going to divide it in half and then shade one of the halves. And then you're going to divide it in half again and shade one of the halves. So now you have a quarter, right? And then you shade, divide it in half and shade one of the halves. And now it's 1/8. And the process keep going. So one question someone would ask is, what is happening to the area of the shaded region? Well, as you can see, it's going to get smaller and smaller and smaller, right? That's the process of taking half. Okay, so if we were tracking the areas of the regions, then we would have a sequence, meaning the sequence of the area of these shaded regions would be The first shaded region is 1/2. The second region is 1/4, right? The third would be 1/8, 1/16, 1/32, and so on. And looking at it on a graph, it will look like that, right? So we can now think of it as a function, and it looks like this is approaching 0, right? So symbolically, what do we write? A sub n, the sequence is an is the sequence of 1/2 to the n power, okay? And we sometimes would put the notation as the sequence, and from 1 to infinity, that's the infinite sequence, is the sequence of 1/2 to the nth power. Okay, so that's how we denote sequence. So what is going on with this sequence? Well, if you think about limit, right, of 1/2 to the n power, well, when n is very large, you have 1 divided by a very large number, and that is going to go to 0. So this sequence will converge to 0, or we say the shaded regions are getting smaller and smaller and smaller, approaching 0. Okay, now that's how we see that as a sequence. Now, what if the question to the same visual is not the individual areas, but what is the sum of all of the areas of the shaded regions? So we are adding, adding. So we have a series, right? It would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 and so forth. And that is what we call an infinite series. Okay, so the question here is asking, if you add up all of these shaded regions, are you going to get a number? And if you are going to get a number, what is that number? Meaning, is this series going to converge or diverge? Okay, so let's take a look real quick. The first sum, and we call that the first partial sum, partial out of the whole infinitely many, right? First partial sum is, and how we write the sum is from sum, that's the sigma notation, from 1 to infinity, right? Because it's infinitely many, 1 to infinity of the sum of what? Of 1/2 to the k power, where k goes from 1 to infinity. Okay, so the first partial sum would just be 1/2. The second partial sum would be 1/2 plus 1/4, and that would be 3/4. Okay, and then the third partial sum would be 1/2 plus 1/4 plus 1/8, and that would be 7/8. Now, when we ask, what is the sum of all the areas? What are we tracking? We're tracking the sequence of these partial sums, okay? The fourth partial sum would be 15/16. So what is going on here? What is the nth partial sum? Do you see a pattern? I would say the pattern is the denominator is 2 to the k power, and the numerator is 1 less, right? So 2 to the k power minus 1. So if you think about what will happen when you add infinitely many of these, meaning what is the limit as k goes to infinity? Well, we can split the fraction, right? 2 to the k power divided by 2 to the k power is 1. So you really are looking at the limit as 1 minus 1/2 to the k power. And you know this is going to go to 0. So we will have 1 as our limit. So then we would say the series converges, and the sum of the areas is 1 square unit if the original area is 1. How nice. Okay, so that is it as far as an overview and how you look at sequences and series. In the next few videos, we'll look at theorems that will help us determine whether a sequence converge or diverge. And then we're going to extend that to series and have a bunch of different types of tests to see if a series will converge or not. Okay, and that is it.